Welcome to Review Lecture 2.1, Gauss's Law. Upon completing this, you should be able to apply Gauss's Law, determine the electric field of various charged objects, determine the electric field inside and outside of conductors. Now think about rain falling on a car. Which would be worse, leaving the window on the roof open or leaving one of the side windows open? Would the area or the size of the window matter? How about the wind? If the rain has a velocity vector v and the window has an area a, the velocity vector v is at an angle theta with the window's normal. Now remember, you always measure angles relative to the normal. The easy way to remember that is we normally measure angles relative to the normal. The flux will then be v times a times the cosine of theta, where flux is the volume flow rate through the window, usually cubic meters per second. The flux is a maximum and equals v times a when theta is 0. That is, v is perpendicular to the window's plane or parallel to the normal. And a minimum equals 0 when theta is 90 degrees. That is, v is parallel to the window's plane and perpendicular to the normal. We asked, would the size of the window matter? A big window is going to be worse than a small window. Okay, how about the direction that the rain falls? The one on the roof, if the rain is coming straight down, the one on the roof is going to be worse than the one on the side window. But if you're in some sort of tornado or hurricane where the rain is blowing horizontally, then the roof window might be okay, but the side window would be a problem. So that's what all of this means. Flux comes from the Latin word for flow, by the way. Okay, so we're going to now talk about the electric flux. And basically what we're doing is we're sort of pretending that the electric field lines are kind of like a flow. So the area vector delta A, this little area vector, okay, delta A, for a small patch or element of the area on a surface is a vector that's perpendicular to the element, that is parallel to the normal, and is a magnitude equal to the area delta A of the element. An electric field vector pierces a small square patch on a flat surface, that's this E here. Only the X component actually pierces the patch. The Y component skims across it. So the Y component does not contribute, only the X component contributes. The area vector of the patch is perpendicular to the patch with a magnitude equal to the patch's area. So the electric flux, delta phi, of an electric field of magnitude E through area delta A is delta phi equals E cosine theta delta A. Or we can rewrite that as E perpendicular delta A or E delta A perpendicular. The units in this are newtons meters squared per coulomb. Okay, so let the elemental areas be small enough that they can be approximated as flat, and they contain a constant electric field through them. We're going to take the net flux through a closed surface, which is used in Gauss's law, and now we're going to find the total flux by adding up all the little elemental areas over the full enclosed surface. The total flux of the surface is going to be given by phi, and that will equal the sum of EA cosine theta. The sum can be replaced by an integral where the integration is carried out over the entire surface. B equals the integral, and this, of course, means over the entire surface of E dot dA. Now, A, of course, is a vector. Now, note the dot product is associated with a cosine. And this would be for Physics 222 students or calculus-based physics students. Most of the time, we don't need this. Most of the time, we just use this. But the surface is called a Gaussian surface. It must be a closed surface. Phi is proportional to the net number of electric field lines that pass through the surface. That means net equals the number of lines out, which are considered positive, minus the number of lines in, and the minus sign is because they're considered negative. Lines pointing inward are considered negative flux, which is the reason for the minus sign. Lines pointing outward are considered positive flux. So it is out minus in. So in other words, here, out minus in. So the dot product in the integral of phi equals the integral of E dot dA can be simplified for a uniform field passing through a flat surface to the sum of EA cosine theta. Theta is the angle between E and delta A. Now remember, it's the angle between E and the normal. Remember, it is the normal to the area that is used when determining theta. Easy way to remember this is angles are normally measured relative to the normal. Now you're going to need this when we talk about optics too. To use Gauss's law to relate flux and charge requires a closed surface. Note the field pierces inward on the left and outward on the right. So the net flux phi is proportional to the net number of electric field lines that pass through the surface. So N out minus N in. Now, a lot of times these will be equal, in which case this will be 0. We'll explain that in a minute. Okay, so we're going to calculate the flux of a closed cylinder in a uniform electric field. Here's the closed cylinder. The electric field, of course, is represented by this blue arrow that's going across the top. Actually, this blue arrow fills the entire volume. So a closed cylinder is placed in a uniform electric field, which is parallel to the long axis of the cylinder. Find the flux to the cylinder. There is no charge inside the cylinder. So we want to find the net flux via the electric field E through the cylindrical Gaussian surface closed by end caps, because it has to be a closed surface. The net flux is a closed integral, can be broken into three parts. And in this case, because we can break them into sums here. So phi will equal EA cosine theta of the left face plus EA cosine theta of the sides plus EA cosine theta of the right face. Now again, remember, angles are normally measured relative to the normal of the surface, not the surface itself. You must remember this or else you're going to screw this up. And you're going to need it again when we get to optics later in the course. Okay, so what we're going to do is we're going to make ourselves a little table. And so here's the end cap on this end. That's the left end cap. So we take the sum of EA cosine phi will be E times the area of that end cap times the cosine of 180 degrees. Why is it 180 degrees? Well, here's the electric field going this way, and here's the area vector going that way. They're opposite to each other. That's 180 degrees. So that the cosine of 180 degrees is minus 1. So it's minus E times A, where A is the area of the end cap. Cylinder B is EA cosine phi, and that will be EAB, that's of course, this is the cylinder itself, E and the area of the cylinder, which is area B, times the cosine of 90 degrees. The cosine of 90 degrees is 0, so that's 0. End cap C is the one on the right here, and that is just EAC cosine 0, so it's positive EA. And why is it's cosine 0? Because the electric field is going parallel and in the same direction as the area vector. So now we combine them up. We just sum them all up. So phi is going to be minus EA plus 0 plus EA. And of course, these cancel out and it ends up being 0. So in other words, what goes in comes out. So the net flux through the cylinder is 0. Everything that comes into the left end leaves the right end. This is a consequence of Gauss's law when there is no charge inside the Gaussian surface. So I actually could have answered this by just when they said this. There is no charge inside the cylinder. Would have told me that the net flux was 0. Okay, so now we're going to take an arbitrary set of surfaces here with some charges inside, and we're going to relate Gauss's law to this. So Gauss's law relates the net flux phi of an electric field through a closed surface, and the closed surface is called a Gaussian surface, and the net charge Q enclosed that is enclosed by that surface. So epsilon naught phi equals Q enclosed. Gauss's law can also be written as epsilon naught times the closed integral of E dot dA equals Q enclosed. Now, a lot of times we can make this approximation of epsilon naught times the sum of EA cosine theta. Gauss's law holds for any closed surface, so pick the one that simplifies the problem. You want one where theta is equal 0 or 90 degrees and is generally centered on the enclosed charge distribution. Remember, only the charges inside the closed surface count. Ignore anything outside, no matter how large. So this means you might want to pick something, if you don't know the effect of a charge, if you can possibly exclude it from the Gaussian surface, you don't have to calculate it, that might be a good idea. Take the algebraic sign of the charges into account when you calculate the net enclosed charge. So in other words, a negative charge is negative and a positive charge is positive. So now we have some examples. We have two electric charges. One of them is positive and the other is negative. And then we have various sample surfaces here. That's represented by this one, this one, and of course the whole thing here. Surface S1, which is the one up here, that encloses a positive charge. The electric field around a positive charge is outward. So the electric field here is outward for all points on this surface. Now think of this as a three-dimensional surface. So thus the flux of the electric field through this surface is positive. So the net charge within the surface, as Gauss's law requires, is E naught phi 1 equals positive Q. Surface S2, which is this one down here that encloses a negative charge. The electric field is inward at all points on the surface because it's a negative charge. Thus, the flux of the electric field through the surface is negative, and so is the enclosed charge, as Gauss's law requires. So epsilon naught phi 2 equals minus Q. Now we go to surface S3. This surface encloses no charge, so Q encloses 0. Gauss's law requires that the net flux of the electric field through this surface be 0. That's reasonable because every field line that comes in passes entirely through the surface, entering at the top and leaving at the bottom. So net flux is 0. So epsilon naught phi3 equals 0. Surface S4 is this one that encloses both charges. This surface, is, however, encloses no net charge because this is positive and that's negative, and they're equal in magnitude. So that sums up to 0. So Gauss's law requires that the net flux of the electric field through this surface be 0. That's reasonable because there are as many field lines leaving the surface as there are entering them. So net flux equals 0. So epsilon naught phi 4 equals positive q minus q equals 0. Now, does the size of the Gaussian surface matter? We're going to investigate various things about Gaussian surfaces. So we're going to pick a point charge because that one's easy to do. We're going to pick two spherical surfaces that are centered on the point charge. So here's surface 1, here's surface 2. They have different sizes. Flux is proportional to the number of field lines passing through the surface. If you look at the surfaces here, you can see that every field line that goes through this one also goes through that one. So the total number of field lines going through the inner surface is exactly the same as the total number going through the outer surface. So this means that the flux is independent of the radius or size of the spherical Gaussian surface. If we doubled the amount of positive charge, we would also double the number of lines passing through each of these spherical surfaces. That would double the flux. If we added an equal amount of negative charge, we would effectively cancel the positive flux, and the number of lines and flux would be 0. So the net amount of enclosed charge does matter. A negative charge would have inward pointing lines and inward flux. Does the shape of the Gaussian surface matter? We're going to pick an arbitrary jagged shape surrounding a positive point charge. The electric field, which is not shown, points radially outward from this charge. The flux is 0 through any of these radial sections. That's the ones that are point radial outward of this surface, because the cosine of 90 degrees equals 0. Only the spherical pieces have a non-zero net flux. The cosine of theta equals 1. And the radial distance of these pieces from the point charge does not matter, because that's what we answered in this question right here. So the sum of the flux through all the spherical pieces equals the total flux, and the shape of the Gaussian surface does not matter. Only the amount of enclosed charge counts. So this means you're free to pick any shape you want as long as it's enclosed. Now here's an example for Gauss's law and Coulomb's law. We're going to derive it for a point charge. And Gauss's law and Coulomb's law actually describe the same thing, the relationship between enclosed charges and the electric field we generate. Here's a point charge. We're going to pick a Gaussian surface, and we're going to pick a spherical surface that is centered on the point charge. Why? Because we want to take advantage of symmetry. We want to make the cosine of theta equal to 0, and we know the magnitude of E is constant on the surface. We're going to divide the Gaussian surfaces into elements of area delta A. Here's a little one of them right here. The elemental flux will be delta phi equals E delta A cosine 0, or E delta A. The net flux through a spherical surface of area equals 4 pi r squared, that's just the area of the sphere, equals sum of EA delta A cosine 0, or E times 4 pi r squared. Gauss's law says epsilon naught phi equals Q enclosed, so that equals E epsilon naught 4 pi r squared, or E equals Q over 4 pi r squared epsilon naught, or K Q over r squared. This is the same equation we got for the point charge using Coulomb's law. We're going to talk about conductors in Gauss's law. In the figure, the object is an arbitrary metal conductor, which we know from experimental evidence contains negatively charged electrons that are free to move. If we assume that the electric field is not equal to 0, a non-zero force equal to E times big E, okay, so the charge on the electron times the electric field, is exerted by the electric field on each electron. So in other words, it's going to make it move if it is non-zero. This will make the electrons move, thus generating an electric current. Electric currents can be detected in several ways. They heat the conductor. They also generate magnetic fields around the conductor. However, we have never observed these effects, so there cannot be an electric field inside the conductor. Now, like charges repel each other, so they move to the surface to get as far apart as possible. So the electric field of the surface of a conductor is perpendicular to the surface. If it was not perpendicular to the surface, the component of the electric field that is parallel to the conductor will make the charges move until the electric field was perpendicular to the surface. And that would create a current, and then we could measure the current. It never happened. Okay, shown in the figure is a charged isolated conductor of copper with a charge Q. Apply Gauss's law to see where the charge is located. Now we figure that EI is 0 inside the conductor. We're going to pick a Gaussian surface just inside the skin. That's the Gaussian, this little black line here. We're going to apply Gauss's law, epsilon naught phi equals Q enclosed, and phi equals the sum of EI delta A cosine 0. Remember that cosine 0 equals 1 and that epsilon naught and A are not 0. We conclude that the only way that EI can be 0 is that Q enclosed has to be 0. This means all of the charge resides on the surface, none of it's inside the conductor itself. That's what this means. This is for isolated conductors in electrostatics where charges by and large do not move. Now we're going to put a cavity inside the conductor. So we have in the figure a charged isolated conductor, copper, with an interior cavity and a charge Q. We're going to apply Gauss's law to see where the charge is located. So EI is 0 inside the conductor, the electric field inside a conductor is 0. We're going to pick a Gaussian surface just inside the skin surrounding the cavity. We're going to apply Gauss's law, epsilon naught phi equals Q enclosed. And then phi equals the sum of EI delta A cosine 0. Remember that cosine 0 is 1 and epsilon naught and A are not 0. We then conclude that the only thing we can say is the Q enclosed is 0. So all of the charge still resides on the outer surface of the conductor. There's no charge on the cavity walls. This is for an isolated conductor, electrostatics, where charges by and large do not move. Now we have an example here. We have a charged isolated conductor, and this is just part of the surface of the charged isolated conductor, and it has a charge of Q on it. The E field inside the conductor is 0, but what is it just outside the surface? So we know that E is perpendicular to the surface, otherwise there would be an electric current as the charge is moved. We're going to apply Gauss's law using a cylindrical closed Gaussian surface. So that's this. And as pictured, this is a cylinder sticking through the wall, through this surface. And we're going to divide the surface into 3 surfaces: the right cap, which is S1, the cylinder itself, which is S2, and the left cap, S3. The net flux is just the sum of phi1 plus phi2 plus phi3, which is the flux through each of these surfaces. Phi1 is this E times A, where A is the area of this cap, times the cosine of 0. And that just equals E times A. Phi2 is EA2 times the cosine of 90 degrees, and that equals 0. Phi3 is 0 because E equals 0 inside the conductor. So the total flux, when you sum it up, is just E times A. We can apply Gauss's law, where phi equals Q enclosed divided by epsilon naught. So E is Q enclosed divided by A times 1 over epsilon naught. We can define the surface charge density as Q enclosed divided by A equals sigma. We're going to give it that symbol. That's a surface charge density. Units on that would be coulombs per square meter. So E, that's the electric field outside a conductor or just at the conductor surface, is sigma divided by epsilon naught. Of course, sigma is the surface charge density. So how about conductors in electrostatic equilibrium? We know the electric field inside a conductor is 0, so EI is 0. The excess charge on an isolated conductor is located on the outer surface of the conductor because, so this is all negative, and these negative charges try to get as far away from each other as possible. They go to the surface. The electric field just outside the conductor surface is perpendicular to the surface and equal to E outside equals sigma divided by epsilon naught, where sigma, of course, is Q over A. That's the surface charge density. And this does not have to be constant over the entire surface. Charge actually accumulates at sharp points on the conductor surface, where the radius of curvature is smallest because it's easiest for the charges to get away from each other there. And later we'll have a problem showing you that. Okay, now we're going to calculate the electric field generated by a long, uniformly charged wire or rod. A long rod is uniformly charged with a linear charge density of sigma equals Q over H. And of course, the units on that would be coulombs per meter. We're going to use Gauss's law to determine the electric field. Now, symmetry indicates that the electric field is going to point radially outward and has a constant magnitude for all points at a given distance r from the rod. We're going to pick a cylindrical surface centered on the rod with height h and radius r to take advantage of the cylindrical symmetry of the field. We're going to divide the surface into 3 sections: the top cap, which is S1, the cylinder, which is S2, and the bottom cap, which is S3. The net flux is just going to be the sum of phi1 plus phi2 plus phi3, where these are the fluxes through each of the areas. Phi1 is 0 and phi3 are 0 because the electric field is parallel to these two surfaces. Phi2 equals phi because, and that equals the sum of E delta A cosine 0. And of course, area of a cylinder is just 2 pi RH. So it becomes 2 pi RH times E cosine 0. And cosine 0 is 1. So it's 2 pi RH E. Phi is then Q enclosed divided by epsilon naught from Gauss's law. We can combine them, condense it with a little bit of algebra. E equals lambda divided by 2 pi epsilon naught times R, or Q divided by 2 pi epsilon naught RH. Now remember, lambda is the surface charge density. Using Gauss's law, we're going to calculate the electric field generated by a thin, infinite, non-conducting, uniformly charged sheet. So an infinite non-conducting sheet is uniformly charged with a surface charge density of sigma equals Q over A in coulombs per square meter. We're going to use Gauss's law to determine the field outside the sheet. Symmetry indicates that the electric field is going to point outward and has a constant magnitude for all points regardless of the distance from the sheet. We're going to pick a cylindrical Gaussian surface that pierces the sheet. We're going to divide the surface into the three sections that we have before. Right cap S1 with area A, cylinder S2, and the left cap S3 of area A. The net flux is just the sum of the individual fluxes through all these areas. So flux equals phi1 plus phi2 plus phi3. Now, the flux through 2, which is this cylindrical surface, is 0 because the electric field is parallel to that surface. Phi1 and phi3 will be the same, and that will equal the sum of E delta A cosine 0, which just turns out to be E times A, where A is the area of either one of these end caps. So the total flux phi is going to be phi1 plus phi2 plus phi3 equals EA plus 0 plus EA, or 2EA, and that equals phi. Phi is Q enclosed divided by epsilon naught from Gauss's law. We're going to compare and condense with algebra. So then the electric field outside a thin, non-conducting, uniformly charged sheet is sigma over 2 epsilon naught, or Q divided by 2 epsilon naught times A. Now we're going to calculate the electric field generated by two parallel conducting plates. So we want to determine the electric field generated by these two parallel conducting infinite plates that are charged with surface charge density of sigma 1 and minus sigma 1, where the absolute value of sigma 1 equals the absolute value of Q over A. In other words, the surface charge density equals Q divided by A, and that would be coulombs per square meter. Okay, now notice one of them is positive, one's negative. That's where this sign comes from. Now, in figure A and B, the plates are isolated, so they're too far apart from each other to influence each other. The charges will then, because these are conductors, the charges are going to distribute themselves on the surface of the conducting plates, and the constant electric field will point outward for the positive plate and inward for the negative plate. Now we're going to move the conducting plates close to each other, and they're conductors, so the charges are free to move. The charges will attract each other to the inward-facing surfaces of the plate because opposites attract. This doubles the surface charge density on the inward-facing surfaces to 2 sigma 1 because all the ones that were distributed over both sides of each plate have now all migrated to the inner side. The outer-facing surfaces are completely stripped of charge, so all the electric field is between the two plates and nothing's on the outside. So we're going to find E inside, the electric field between the two closely spaced plates, and we're going to apply Gauss's law to do this. We'll pick a cylindrical surface S, which has caps of area A. The only point of the Gaussian surface that has flux passing through it is the vertical cap right here in the gap between the plates. That's this right here. This cap has surface area A. This one here, okay, the cylinder itself, okay, the area is parallel to the electric field, so it's 0. There's no electric field inside the plate, so that's 0 there. So the only one you have is this cap right here of area A. Gauss's law says sigma equals EIA, or Q enclosed divided by epsilon naught equals 2 sigma 1 A divided by epsilon naught. So between the plates, the field is constant. EI equals 2Q divided by A epsilon naught, or 2 sigma 1 divided by epsilon naught. Outside the plates, we're going to use a Gauss's law on the cylindrical surface S prime. Find EO, the electric field outside the plates. B equals EOA equals Q enclosed divided by epsilon naught equals sigma 1 minus sigma 1 times A divided by epsilon naught equals 0 from Gauss's law. Where does this come from? Well, surface charge density on the positive plate minus the surface charge density on the negative plate. The minus sign comes from the negative plate. So outside the plates, the electric field is 0. Now, this useful result is a capacitor. A capacitor way that you can store energy inside the electrical field between two parallel plates. Outside the plate, the electric field is 0. It's all inside, all the actions between the plates. Now we're going to use Gauss's law to prove the shell theorem and find the electric field generated by a shell of charge Q of radius r. This gray area here, this faint gray dotted area, is the shell of charge Q. Inside the shell, we choose a spherical Gaussian surface S1 of radius little r that's less than big R. Of course, big R, of course, is the radius of the shell. And the center will coincide with that of the charged cell to take advantage of the symmetry of the situation. Gauss's law says Q enclosed has to be 0, and sigma has to be EI times A, and that equals Q enclosed divided by epsilon naught, and that equals 0. Why is Q enclosed equal to 0? Well, the Gaussian surface we picked is entirely inside the shell, and there's nothing inside the shell. There's no charge inside the shell, so that means Q enclosed equal to 0. So the electric field inside the shell is 0. That's shell theorem number 1. Outside the shell, we use a spherical Gaussian surface S2 of radius r bigger than the radius of the shell, whose center coincides with that of the charged shell. The area of the surface, A equals 4 pi r squared. Q enclosed is then equal to Q, and B equals EI times A. That equals Q enclosed divided by epsilon naught, or Q divided by epsilon naught, because all of the shell is inside this surface, and the shell carries charge Q. This equals E outside, the electric field outside, times 4 pi r squared, which is the area of the Gaussian surface. So E outside, the electric field outside a shell, is Q divided by epsilon naught 4 pi r squared, or KQ over r squared. This is the same equation as for a point charge. So the electric field outside a shell of charge is the same as that of a point charge with the same charge located at the center of the shell. That's shell theorem number 2. So there's a recipe for applying Gauss's law. You can't go wrong with reading the problem, writing down the knowns and unknowns, and making a sketch of the charge distribution. Identify the symmetry of the distribution and its effect on the electric field. Gauss's law is true for any closed surface S. Choose one, we're going to talk about that on the next slide, that makes the calculation of the flux phi as easy as possible. In other words, work smart, not hard, and be creatively lazy. Use Gauss's law to determine the electric field vector. Now, how to choose a Gaussian surface? You should pick a surface that, 1, makes an angle between delta A and E equal to 0 or 90 degrees. You want A perpendicular to E or A parallel to E. Remember, angles are measured relative to the area's normal. Don't forget that. People screw that up all the time. You should pick a surface that 2, so the magnitude of E is the same at all points on the Gaussian surface, so E can be brought out in front of the summation or the integral. You should pick a surface that 3 takes advantage of the full advantage of the symmetry of the electric field. You should choose a Gaussian surface that 4 is easy to calculate the area, like a sphere, which equals 4 pi r squared, or a cube, 6a squared, or a cylinder, 2 pi r L. Remember, you want the area, not the volume. Okay, checkpoint. In July, Joe set up his fixed array of solar panels to maximize the amount of electricity output from the array when the sun was high in the sky. Unfortunately, Joe finds that the array in winter doesn't cooperate very well. Even though there's nothing physically wrong with the array, what is the most likely cause of Joe's winter problem? A, less sunlight reaches the Earth during winter months. Well, actually, the sun is actually closer to the Earth during the winter than it is during the summer in the northern hemisphere. That's because the eccentricity of the Earth's orbit. The winter is caused by the axial tilt of the Earth, not by how close the Earth is to the sun. So in reality, you get slightly more sunlight during the winter months over what hits the Earth total than you do during the summer, because the Earth is actually closer to the sun. B, the sun is lower in the sky during the winter, so sunlight strikes the solar panels at a glancing angle. Remember that idea about flux and parallel to the normal? B's looking pretty good here because the sun is lower in the sky during the winter by quite a lot. C, the average temperature is much colder during the winter months. That has nothing to do with the solar array. D, more sunlight is absorbed by the atmosphere during the winter months because the sun is much lower in the sky. It does go through a thicker layer of atmosphere, so D is a possibility too. E, the sun is not as bright during the winter months as it is during the summer. The sun is the same brilliance all the time. The sun doesn't change. Actually, the sun's getting warmer as it ages, but that's not pertinent to this problem. B is a more important effect. The sun is lower in the sky during the winter, so the sunlight strikes the solar panels at a glancing angle. The difference between the sun angle between the summer solstice and the winter solstice is twice the axial tilt of the Earth, so it's a 47-degree difference. That's quite a lot. A more minor effect is more sunlight is absorbed by the atmosphere during the winter months because the sun is much lower in the sky, so it's going through a thicker layer of atmosphere. That's a minor effect, but both of those have some effect. So what would Joe want to do? He will want to put his array on some sort of gimbal so it would tilt to follow the sun as it goes across the sky, which he should do that anyway, because then he'll get much better efficiency out of this. Okay, consider the 5 situations shown. Each one contains either a charge Q or a charge 2Q. A Gaussian surface surrounds each of the charged particles in each case. Considering the electric flux through each of the Gaussian surfaces, which of the following comparative statements is correct? Well, Gaussian surfaces have to do with the enclosed charge. So I look for, and it looks like they're looking for equal to or greater than. So you want the biggest one first. The biggest one first are going to be the ones that have the biggest charge inside. So case 2 and case 4 are going to be the 2 biggest ones. And it's only the charge inside that counts. So these 2 will be equal to each other. So I'm looking for 2 equals 4 to be the first things here. And this one is the only one. Also, I know that because the enclosed charge in this is less than this, and these 2 are equal to each other, so case 1 equals case 3, so it's 2 equals 4 is greater than 1 equals 3, so A is the correct answer. Flux depends only on the enclosed charge, not on the shape or size of the Gaussian surface. When a particle with charge Q is surrounded by a spherical Gaussian surface, the electric flux of the surface is Vs. Consider what would happen if the particle was surrounded by a cylindrical Gaussian surface or a Gaussian cube. How would the fluxes through the cylindrical, phi cylindrical, and cubic, phi cubic compare to phi s? The shape doesn't matter, the size doesn't matter, so they're all going to be equal. The flux depends only on the enclosed charge, not on the shape or size of the Gaussian surface, which makes it a very powerful way of calculating things like this. A spherical Gaussian surface of radius r is surrounding a particle with a net charge q. If the spherical Gaussian surface is replaced by a cube, under what conditions would the electric flux through the sides of the cube be the same as through the spherical surface? It doesn't matter. Flux depends only on the enclosed charge, not on the shape or size of the Gaussian surface. Using Gauss's law, find the approximate magnitude of the electric field at the surface of a cube that has 0.1 meter sides and a uniform volume charge density of rho equals 2 times 10 to the minus 9th coulombs per cubic meter. Hint, the volume charge density is the amount of charge per unit volume. It turns out to be F, 3.8 newtons per coulomb. D equals 0.10 meters. Rho equals 2 times 10 to the minus 9th coulombs per cubic meter. Q equals rho times d cubed. That is the charge density, volume charge density times the volume is the total charge. And A equals 6d squared. That is the area of the outside of the cube. Gauss's law says phi equals EI times A equals Q enclosed divided by epsilon naught. We're going to solve for the electric field. E is Q divided by A epsilon naught. We substitute in for Q, which is rho d cubed. And of course, the area is 6d squared, and we have the epsilon naught. We cancel out some of the d's. We wind up with d times rho divided by 6 epsilon naught. So d is 0.10 meter. Rho is 2 times 10 to the minus 9th coulombs per cubic meter. We have the 6 coming along, and here's the epsilon naught. It comes out to be 3.8 newtons per coulomb. Gauss's law may be written as phi equals the sum of E perpendicular delta A or Q enclosed divided by epsilon naught. Which of the following statements concerning the charge Q enclosed is true? The charge Q encloses the sum of all charges. No. The charge Q encloses the sum of all charges on the Gaussian surface. No. The charge Q encloses the sum of all charges inside the Gaussian surface. That one's looking pretty good, but don't stop there. Always read everything. The electric field due to Q encloses zero inside the Gaussian surface. Not necessarily true. The charge Q encloses the amount of charge present whenever the electric field is constant. No. So D is no, E is no, A and B are no. C is the only correct answer. The charge Q encloses the sum of all charges inside the Gaussian surface. Only enclosed charges count. Now, where would you go during a lightning storm? Hint, Gauss's law on conductors. Why is this the safest place? And you've heard any myths about why this is the safest? I love to bust myths. The answer to the first question is you want to be inside a metal object such as a car. Why is this the safest place? Because the charge stays on the outside of the conductor. You're safe inside the conductor. Have you heard of any myths about why this is the safest place? One of the myths is that rubber tires insulate you from the charge, and that's a very popular myth. By the way, it's not going to protect you from a lightning bolt. First of all, look at the arc on this front tire. Now, these are older fashioned tires. This is an old car. Tires back then weren't very good conductors. Now we have tires that are steel belted radials. They have carbon in them. It's deliberately made to be good conductors. That allows the charge that builds up when you drive the car, that accumulates on the car body while driving, that allows that charge to safely drain off quickly enough so it doesn't spark and ignite gas vapors while you're fueling. Later we'll have a demonstration problem to show you why this is. Thank you.